In this video, we're going to build the quadratic Taylor approximation to a complicated function, cosine, at a specific point. And remember, whenever we're building these approximations, linear approximations, Taylor approximations, they're always centered at one location on the graph of the complicated function. We need that as a reference point. As a first step, we should remind ourselves what the approximation is. You do need to memorize this, so try to get a little ahead of me here in copying out the formula for the quadratic Taylor approximation, or you could also call it the degree 2 Taylor polynomial. Those are exactly the same thing. Think of that and filling that in yourself as we move from left to right here. The approximation for degree 2 Taylor polynomial is at the point x equals 0. Often this is written as a in the general case, but here we have a specific point already. We're going to approximate this formula with the point value at 0 plus the slope at 0, and I'll put all the details in here from the general case. That's our a again, x minus a, and this whole thing here is our slope. And the quadratic part of this comes in last. It's the second derivative at 0 and x minus 0 squared. So again, we have that matching of the derivative with the value there. And don't forget the scaling factor over 2. Again, we see 2's, 2's, and 2's. If you like to think of it as 1 power 1 divided by 1, that can also help. So you feel like there's a general pattern to all the terms. So that tells us what we need. We're missing currently all of these function values, the value of the function, the derivative, and the second derivative. So very much like an exercise in linear approximation, we start with our function and recognize that we need the derivative as a formula. The derivative of cosine is negative sine, and then we need the second derivative, so we differentiate again. The negative we copy, and the derivative of sine is cosine. We then need that evaluated at 0 for all these points here. So f of 0. What is the height of the cosine function at 0? It is 1. What's the slope of the cosine function at 0? Well, it's negative sine of 0, but sine of 0 is 0. What about the second derivative, the concavity? We're going to have negative cosine of x, and that is negative 1. So what we get is a height of 1. We have a slope of 0, and we have a concavity, negative 1, concave down with a certain bend to it. That tells us information about the graph of the cosine function at the point 0, and then we're going to build that into a quadratic approximation. So what we can say is cos of x here is approximately equal to f of 0 is 1 plus the slope. I'll put all the gory details in one more time here. The slope was 0 plus the concavity, negative 1, over 2, that comes from the outside, and then x minus 0 squared, or with all the zeros we can tidy up, we end up with 1 minus x squared over 2. And if you think about that for a moment, the cosine function, without a calculator, you would not be able to compute anything there. But if you wanted to get a good approximation to the cosine function, this is a polynomial that anyone can calculate just with addition and subtraction and multiplication. So we've translated a transcendental function, the cosine function, one that we really need some serious technology to be able to evaluate, and traded it in for a good approximation, at least near 0, which is something we could do with pen and paper. So this is a powerful tool and actually underlies a lot of what happens in computers when you try to evaluate functions like cosine. For now, let's stick with visualizations. If we imagine our graph here again, we have the cosine function, looks like this. We have pi over 2 and 1 and negative 1. We already found earlier the first degree Taylor polynomial, or the tangent line, or the linear approximation, would be a horizontal line if we made those approximations at x equals 0. So that's our linear approximation, or the Taylor polynomial of degree 1. Something you've seen before, just now giving it this new label. Our new ingredient is the function y equals 1 minus x squared over 2. And that is a parabola. It is shifted up by 1. So it's a usual parabola moved up by 1, flipped upside down so it opens downwards. So that's perfect. That matches the concavity of our graph. And it has some details here. For our sketching purposes, though, we know that the construction was built so that the slope and the concavity of this red line, which is our Taylor polynomial of degree 2, was built so that this polynomial matched the slope and the concavity of the blue lines. And what we see out of there is quite a nice approximation. Now, we can get a little more convincing than this sketch if we go to the next page. Here we have, flipping the colors, the linear approximation here in red. So that's a horizontal line. And compared to the black line, that's our reference point. That's the cosine graph. The black line and the red line, they're similar around here. If you zoomed in, you'd say, yes, the graph in black is almost flat, and so the red line's a good approximation. But if you go further down the curve, or imagine looking at values between 0 to -1 or all the way out to +1, if you look at the black line, which is what we're trying to approximate, and the blue line, those are almost on top of each other, even as far out as here. We get a really high quality approximation, even though all we've matched is the slope and the concavity at this point x equals 0. As we know, the function is not going to stay close to the parabola forever because the cosine graph eventually is going to turn away while the parabola would keep going. But for a larger region around x equals 0, we get a high quality approximation out of this second degree Taylor polynomial. Much more well informed about the shape than the simple linear approximation that we've seen earlier. And that points to the power of this technique of not being limited to just linear approximations, but using higher derivatives, second derivatives, to get a higher quality fit. Now there's a technical detail, of course. We had that approximation, which was that our function is approximately f of a plus the slope. Again, try to fill this in your own mind as we go through it. That'll help you to remember it. We had this interesting ingredient over here, which was this dividing by 2 part. Now, why would we do that? Well, let's change this a bit and give this a name. This is a parabola. This entire contents here is a parabola. Let's call it P2, 2 for degree 2, P for polynomial. That's our polynomial of degree 2. What are the properties of that function? Well, if we just were given this, and then we did a quick little analysis and ask, well, what's the derivative of this quadratic that we have here? We can do that calculation if we're very careful and remember that all of these f of a's, f prime of a's are constant with respect to x. If x is our variable, and it is, when we talk about this parabola, it's a parabola with x being the independent variable, then all of these other f prime, f double primes are just numbers that we would have calculated earlier. If that's the case, then when we take the derivative, we would get 0. We would have f prime of a, and this derivative x minus a constant is just 1. And then we would have the second derivative of a, that's just a constant over 2. And notice what happens here. The 2 comes down, and we'd have x minus a to the 1 lower power. Again, this can look odd unless you remember that x is the variable that we're differentiating with. Everything else that has a's in it is just either a constant multiplier or a constant by itself, and we use the standard derivative rules for those. And you'll notice what we get here. If we differentiate this polynomial, we differentiate this quadratic, and we evaluate it not everywhere, but specifically at the point A, let's fill in the blanks. We're going to get 0, we're going to get f prime of a, and we're going to have f double prime of a over 2 hanging around. Oh, the 2's actually cancel, so we can get rid of that. Cancel, cancel. But we have x minus a, but we're plugging in x equals a, so we get an a minus a. That's going back to the centering at the point we're interested in. And that means all of that simplifies to 0. So what is special about this polynomial at the point A? Its derivative of our polynomial is exactly the same as the derivative of the function we're approximating. They have that in common. In fact, we already used that information with the linear approximation. We said we want to build a linear approximation, these two terms here, so that the slope of the function and the slope of the line we're building are identical. It turns out the same thing will be true for the second derivative. If we go down, here's our function in general. We take the derivative of 0, we get 0. We take the derivative of f prime of a. Remember, a is just a constant, so we get a 0 there. And we take the derivative of this term, f double prime of a is a multiplier of x. And so we just get that times 1. Well, that's just f double prime of a. So what we just found is our polynomial, P2, has the same concavity as the original function, f of x, at the point x equals a. Let that sink in for a second. Graphically, what we're saying is if we had our polynomial here, a nice parabola, it and the function we're approximating have the same bend in the functions as each other, at least at that point. The other graph can deviate later, that's fine, but at that point they both bend down to the same extent, and that gives us a pretty good model, at least in the short term, for the quadratic matching the more complicated function. But that is only true, going back through these steps, because we had this 2 in the denominator, and that 2 got canceled with the 2 when we differentiated the x minus a squared. This little cancellation was required to get this result, and that's why we have the 2 in the denominator. If we don't have that 2, we don't get the same second derivative for our polynomial as our function. We would get off by a factor. So we don't need that for the first derivative. It happened by itself because there was no multiplying when we took the derivatives. But when we differentiated the squared term, we got a 2 for free. We need to get rid of that. And so that's why the f double prime term has divided by 2 associated with it. We explore this not because we expect you to be able to reproduce this argument, but just to give you a rationale rather than hand-waving for why, as you go down these terms, you would have this kind of multiplying factor adding in that don't seem to be there for the constant linear terms. Of course, we can always go further, right? We have this great insight that linear to quadratic improves the quality of an approximation. Well, what might we do instead? Well, we might go to, for a second, hey, let's go to a third degree polynomial. Why not? There's no reason we have to stop keeping from this pattern. And the nice thing about the third degree Taylor polynomial is it would be exactly the same pattern we've seen so far. We would see the linear approximation, or we might call it P1 of x, the first degree Taylor polynomial. And then we could add our second degree polynomial with the over 2 and x minus a squared. That captures the second derivative information. So that would be our P2 of x. And if we wanted to add a third term, you can imagine it would share the third derivative information. We would have a cubic term as well. And then, thinking back to the last slide, what would we put under this? Well, if you think of differentiating this P3 a few times, we get a 3 down front, then that would turn into a 2, then we get a 2 down front, that would turn into a 1, we get a 1 down front. We would want to cancel all of those, so we'd end up dividing not just by 2, but by 3 times 2, or some people have seen this notation, 3 factorial. And you'll see that if you look in the textbooks for the general pattern for Taylor polynomials. We can actually go to 4th degree and 5th degree. In fact, we can build a whole series out of this that can be infinitely long. For our purposes, we're pretty much going to stop at cubics, but this pattern can be extended further if it makes sense. It'll just keep increasing the amount of work you have to do, but also increasing the quality of the approximation. So that's our idea. We had the inspiration that a linear approximation could be useful for approximating complicated functions. And then we said, well, why stop at linear? Let's go to quadratic, and recognize now that we can go past quadratics into cubics. You'll see practice problems that use this kind of skill, just building them mechanically. And we're also going to see how to look at these polynomials and then use that to give some insight into the original functions. We will try to connect these ideas back to what we've seen earlier in graphing functions in several different ways to try to reinforce the underlying ideas here.